We are in Chapter 1, Section 2. This is the 8th session, and we'll be discussing stress in oblique planes, factor of safety, and examples. In the end, we give a summary of Section 2. This is the last session in Chapter 1, and also the last session in stress and axial loads. So after this session, we'll start strain. Here we'll discuss maximum and minimum normal and shear stress acting on an element. We initially took a bar subjected to axial loads as shown. We then took a section perpendicular to the axis of the bar at C1. The centroid of section C1 was denoted as C, and we found out the variation of stress at the point C as an element is rotated. We could have taken any other point for our investigation. Apart from the section at C1, we took different inclined sections at different angles, all passing through the point C. We initially considered an element at point C with one of its face aligned with the section at C1. We then considered different oblique cuts and the element at C with its face aligned with an oblique cut. This way, we could find the variation of stresses of an element at the point C as it is rotated. In order to define the rotation, consider this line perpendicular to the left face. Here is 0. An anti-clockwise rotation of this line is considered positive. We found stresses acting on the element at theta is equal to 0, theta is equal to minus 30, theta is equal to minus 45, and theta is equal to 30. At theta is equal to 0, the left face of the element coincides with the section at C1. We have earlier discussed that the stresses acting on this left face of the element is P divided by A. If we look at the normal stresses acting in these three elements, we'll see that this stress P divided by A is the maximum. Now for this element, sigma y is 0. And if we look at the normal stresses again for these three elements, we'll find that the sigma y in this element is the minimum. For rotation by any other angle, we'll still find that this is the maximum normal stress and the sigma y here is the minimum normal stress. As we can see, there's no shear stress in this element. At theta is equal to minus 30, the shear stress here is 0.433 P divided by A. And also as at theta is equal to 30 degrees, the shear stress is of the same magnitude, but it's oppositely directed. At theta is equal to minus 45, the shear stress on the right face is 0.5 P divided by A, which is the maximum you can see in these three elements. The shear stress is anti-clockwise and therefore positive in the right face. If theta was plus 45 instead of minus 45, then the magnitude of the shear stress would have been the same. And however, the direction of the shear stress would be opposite. So on the right face, we'll get a negative shear stress. Again, if we rotate by any other angle, this shear stress on the right face remains the maximum positive shear stress acting on the element. And at theta is equal to 45 degrees, we'll get the maximum negative shear stress acting on the right face. When we mention theta, we can talk about the rotation of the whole element or the rotation of a face of the element. Considering the right face, we can say that the maximum and minimum principal stress occurs at theta is equal to 0 and theta is equal to 90. And the maximum and minimum shear stress occurs at theta is equal to minus 45 and theta is equal to plus 45. The planes of maximum, normal and shear stress and their values can be obtained using the equations that we determined earlier. So the normal stress sigma was given by this expression. Using d sigma divided by d theta is equal to 0, we get the planes at which maximum and minimum normal stress occur. So this expression gives us the planes at which the maximum and minimum normal stress occur. When theta is equal to 0, sine theta is 0. And when theta is 90, cos theta is 0. So the planes are theta is equal to 0 and theta is equal to 90. When theta is equal to 0, we get sigma is equal to P divided by A, which is the maximum value. And when theta is 90, we get sigma is equal to 0, which is the minimum value. These same values were obtained earlier. The expression for shear stress was given earlier as shown here. D tau divided by d theta is equal to 0 gives us the planes at which maximum and minimum shear stress occurs. The planes at which maximum and minimum shear stress occurs is given by this equation, or when tan square theta is equal to 1. That is at values of theta plus and minus 45 degrees. At theta is equal to minus 45, we have the maximum shear stress plus 0.5 P divided by A. At theta is equal to plus 45, we have the minimum shear stress acting of minus 0.5 P divided by A. We have carried out this discussion by limiting rotation between plus 90 and minus 90 degrees. We took a simple case, a bar subjected to axial force, and we took up the element in the bar, saw how the stress varies as the element rotates. Some of the trends that we found out are generally applicable. So they are applicable to any point in a structure under any loading. Later on, we will do a thorough investigation into transformation of stresses, where we'll derive formulas that gives us an indication of this behavior. Case we dealt with, we found that at theta is equal to 0, element was subjected to the maximum normal stress as well as the minimum normal stress, and that shear stress was 0. The maximum normal stress and the minimum normal stress is known as the principal stresses as well. So we can say that at theta is equal to 0, the element was subjected to the principal stresses as well as 0 shear stress. If we rotate the element by minus 45 degrees or 45 degrees, then the element is subjected to the maximum and minimum shear stress. In general, we'll see that the principal stresses do not always act when theta is equal to 0. So theta can be a given angle, say alpha, but the other factors remain the same. That is, the maximum principal at that angle will act, and the minimum principal stress will act, and that shear stress will be 0. Now, if that angle is alpha, then if we rotate the element to another 45 degrees, so 45, alpha minus 45 or alpha plus 45, then we'll get the maximum and minimum shear stress acting on that element. There will also be some normal stress, sigma x and sigma y, acting on the element. So even though we have looked only at a straightforward case, we have been able to study some of the features of transformation of stress, mainly physically. Till now, we have dealt with cases where components have been subjected to only normal stress or component have been subjected to only shear stress and looked at corresponding examples. Here is an example where the component is subject to both normal and shear stress. So here we have a wooden piece which is glued along this black line. It is subjected to a force P. The dimensions are given and the allowable stress in tension is given. To start with, we find the area of perpendicular section, which here is 70 by 100. We then divide that area by cos 20 to find the area of the inclined section. We can resolve the force P perpendicular to the inclined section and parallel to the inclined section. So the force P perpendicular to the inclined section would be P cos 20, which divided by this area should be equal to 30 MPa. From the equation, we can find the value of P. Once we have found the value of P, then P sine 20 divided by this area would give us the shear stress act. Here we have another example. This is a circular tube. The inner portion is hollow here, and the load applied is 375 kilonewton. The weld is at an angle, so we need to find the normal and shear stresses acting on the weld. To start with, we find the area perpendicular to which the force acts. So from the radius of this annular circle, we can find out the area. Once we have found out the area, we divide it by cos 30. We know the area of the weld. We then resolve P into a force that is perpendicular to the weld and a force that is along the weld. So P cos 30 would be perpendicular to the weld. Divide by the area of the weld, give us the normal stress. P sin 30 P along the weld and divide by the area of the weld will give us the shear stress acting. Here we deal factor of safety. With most of the cases we have dealt with till now, we were given the loads applied to the structure and asked to find stresses in members. We also dealt with some cases where we were given the maximum allowable stress and asked to find out the maximum load that can be applied. Consider a bar subjected to tensile load. If we increase the load, then the bar will fail at an ultimate load, or the load will decrease after reaching an ultimate load. The stress associated with this ultimate load is the ultimate stress. Components can be tested under direct shear to find out the ultimate load in shear. Circular tubes under torque can also be tested. From the ultimate load in shear, we can get the ultimate stress in shear. Now, factor of safety can be given in two different ways. So, factor of safety can be given as ultimate load divided by allowable load, or factor of safety can be given as ultimate stress divided by allowable stress. In the factor of safety method, the uncertainties dealing with load and the structure is dealt with in one factor. There is another method known as the load and resistance factor design method, where the factor of safety of live load, dead load, and of the structure are dealt differently. In the LRFT method, PU is the ultimate load capacity. And if this equation is satisfied, then the load is deemed as safe. Gamma L here is the live load factor. LL is the live load. So in a floor in a building, the inhabitants of the floor form the live load. Gamma D is the dead load factor. And DL contains all the concrete and steel and other materials. Phi is the resistance factor that is related to the structure. Here we have a factor of safety problem. There's a force P acting. This is a steel loop and AC is an aluminum rod. The four portions of the loop are equal in length. We understand that the tension in the loop will be the same. To solve the problem, we can consider joints in B and A as in the case of plain trusses. We need to find out the maximum load P that can be applied without failure. So we need to find out which fails first, that is the steel loop or the aluminum rod, and based on that we can find the force P. So first let us look at the joint B. We need to know the angle to solve the joint, and tan theta would be 450 divided by 250, from which we find the angle to be 60.94 degrees. Here we see that 2p cos theta is equal to p, from which we get p is equal to 1.03 p. Now let us look at the joint A. This angle is 90 minus 60.94 degrees. So here we get 2p cos this angle is equal to FAC, from which we get FAC is equal to 1.8p. Let us now find the maximum force in the loop. The loop is 20 millimeter in diameter, so this is the area into the ultimate stress, which gives the maximum force in the loop. Here we find the maximum force in the aluminum bar. This is the area into the ultimate stress, and this gives the maximum force that can be applied in the aluminum bar. We see that the maximum force in AC will govern failure. This is equal to 1.8p, from which we get a value of p. The force in the loop is 1.03p, and we get this value. This value is less than the maximum force that the loop can withstand. If instead we took the maximum force in the loop, then we'll find that the force in AC will be greater than this value and AC will fail. So P based on this value is the maximum P that can be used. Dividing by the factor of safety, we find that the maximum load is 39.28 kilonewton. Here we have another factor of safety problem. We are required to find the cross-section of AB considering a factor of safety of 3. To start with, we can take moment about point 2 in the bar BCPE and find out the reaction at B, since this load and this load are given. So we find out the reaction at RD. In order to find out the force in AP, the force acts along the axis. So we know the direction. We need to find out the moment arm to find the force acting in AP. So here BD is 1.3 meter. This angle we know is 40 degrees. So using sine, we find x dash, which comes out as 0.836 meter. Now we take moments about D. So we know the distance x dash. So the moment arm of RP is known, and we can find out RP. The ultimate stress is given as 450 MPa divided by 3, the factor of safety. The allowable stress is 150 MPa. So divide the force by the allowable stress, get the required area of AB. We look at a problem here where we have to find the factor of safety rather than the factor of safety being given. So here we have a force 50 kN acting, and there are two links at PE and two links at CF. We are given the ultimate normal strength and shear strength. To start with, we look at the equilibrium of the member EFG. So we can take a moment about the point E to find the force acting at F, and we can take moment about F to find the force acting at E, as we have done here. So this is the free body diagram. So here we have given the forces in FC and EB. We next find the capacity of the members and of the poles. So the capacity of the link CF is this is the dimension. There are two links, and this is the maximum normal strength. So this is the capacity of the two links. We have these poles in double shear, and this is the diameter of the bolt. So this is the area into 2 into the ultimate shear strength. So this is the capacity of the bolts. We find that the capacity of the bolts is lesser. The force in FC is higher, so the factor of safety is the capacity of the bolts divided by the force in FC, which we get as 2.618. Here we have a problem involving the load and resistance factor design method. So in this case, we have to find out the live load, but instead of one factor of safety, there are three different factors. So there's already a load 65 kgs acting here. The weight of the beam is 35 kgs, and the ultimate strength of AC is 15 kN. This is the dead load factor, this is the live load factor, and this is the resistance factor for the structure. To start with, we'll need to find the angle here, and then the perpendicular drop from B to BC. So this is 2, this is 3.5. So we get the angle using tan theta, which we get as 29.744. Now in here we have the angle now, and this is 3.5, so we can get x dash. So we get x dash is equal to 1.736 meter. Now the perpendicular distance of FAC from B being known, we can consider moment about B to find out the maximum load that can be applied here. So this live load multiplied by 1.5 multiplied by 9.81 into the distance 3.5 plus 65 into the dead load factor into 9.81 into again 3.5 plus 35 into the dead load factor into 9.81 into half of 3.5 is equal to FAC into 1.736 into the resistance factor for the structure. Now FAC is 15 kilonewton, from which we get the live load as 361 kgs. The live load of 361 kgs acting here, we can find out the factor of safety. Then here again, we have 361 into 9.881 into distance plus 65 into 9.81 into distance plus 35 into 9.81 into half of 3.5 is equal to FAC into 1.736, from which we get a value of FAC. The ultimate strength of AC is 15 kN, from which we get a factor of safety. We summarize the second section here. This is done in two parts. In the first part, we deal with analysis of members, and in the second part, we deal with stresses. This will help us untangle the stream of issues. Let us discuss the first section initially. In the first section, we dealt with statically determinate stresses and frames. The whole structure was considered, and using equations of equilibrium, we found out the external forces acting. In plane trusses, we then used the method of joints to find forces acting in members. In plane frames, we use the method of members to find out forces acting at different points on members. Here we deal with normal stresses acting in perpendicular sections of members for a number of cases. Hence, we need to find out the axial forces acting in members. We have had cases where the forces act on joints, and as such, we have used the method of plane trusses. In one case, we used the method of plane frames. In other cases, equations of equilibrium can be directly used to find the forces in members. We have not only dealt with normal forces and stresses, but also shear forces and shear stresses, as in bolts. Most of the problems we have dealt with has either been normal stress problems or shear stress problems only. In the end, we have dealt with cases where there is both normal stress and shear stress acting. We realize that we are dealing with simple cases. Loading in structures can be more complicated, and stresses in perpendicular sections of members can be complex, comprising of both normal and shear stress. Most problems we have dealt with has involved loads being given and stresses being needed to be found out. However, there has been problems where the allowable stress has been given and we have had to find out the maximum allowable load. When it comes to normal stresses, perpendicular sections in axially loaded members have the highest normal stresses. So the allowable normal stresses can be directly used to find out the maximum loads that can be applied. This is done by equating normal stresses in perpendicular sections to the normal allowable stresses. We have also dealt with factor of safety cases. The ultimate strength divided by the factor of safety gives the allowable stress which can be used. We now discuss stresses. Consider a body subjected to a number of forces. Let us take a section AA as shown. Then the portion of the body would be in equilibrium under the forces that act on that portion and a resultant acting on the section. However, the resultant comprises of small forces that act throughout the section, such as section AA here. Let us consider a small area del A and let the force acting on that area be del P. Then stress is defined as limit del A tends to 0, del P divided by del A. We can resolve del P into a vertical force and a horizontal force, del F and del P. Then the normal stress is defined as sigma is equal to limit del A tends to 0, del F divided by del A. And the shear stress tau is defined as limit del A tends to 0, del V divided by del A. Now, at a point in a structure subjected to external loads, there can be infinite planes that pass through that point. So infinite values of stress can be given at that point. In order to give the state of stress at a point in a body, we first consider a coordinate axis as shown here. Say that we want to define the stress at a point M in this body. We then consider an infinitesimal element at the point M. The faces of the element align with the faces of the coordinate axis. We then take sections of the body parallel to the planes of the coordinate axis and passing through the point M. In this figure, we have taken a section parallel to the YZ plane. This arbitrary force is resolved into forces acting along the X, Y, and Z direction. This arbitrary force is considered for an area del A. Setting del A tends to 0, we find out the stresses acting. In this manner, we find out the state of stress at the point M. In many cases, the stresses associated with the Z coordinate is 0. Then we can represent stresses using this square two-dimensional element. It can be shown that tau xy is equal in magnitude to tau yx. We have talked about stresses in members on one hand and stresses in elements on the other. The two ideas are brought together when we consider stresses in elements aligned with the faces of sections. A fair bit of our discussion with analysis of members has involved taking perpendicular sections. So initially we discussed the stress in an element as shown here with its face aligned with the perpendicular section. We then take oblique sections and find out the stresses on the elements with its face on the oblique section. The stress variation of an element as it rotates is discussed. In a bar subjected to axial force,